Hello, my name is Nick Zampa and I'm a product manager at Waters. Today, I'd like to present Be Prepared, rediscovering fundamental tools for improved purity and recovery in preparative reverse phase HPLC. In the next 30 minutes or so, I'd like to speak with you about some practical considerations for your day-to-day purifications. Some of these ideas you probably already know about or use routinely, but it's useful to step back and think again about what we are doing and why we do certain things. The things we talk about today will help you attain higher purity and increased recovery. We will discuss general principles. In doing so, we will touch on the basic purification process, defining the purification problem, and examining protocol options. We will also address some practical considerations for improving the resolution of purification runs and increasing your mass capacity. With respect to improving resolution, we will highlight some fundamental chromatographic principles, such as efficiency, retentivity, and selectivity. However, we will address these in the context of purification, as opposed to analytical chromatography. When addressing mass capacity, we will talk about both the physical and chemical characteristics of chromatography that can be utilized to alter mass capacity. Throughout this presentation, I will highlight key resources that Waters offers to support you in selecting your column, scaling up your method, and designing optimal methods. Before we can examine the experimental levers we have to achieve the desired purification, it's important to take a step back and examine the basic purification system flow path. We have a complicated crude reaction mixture and wish to get enough purified material for the next experiment in the drug discovery workflow. We all know what the purification system looks like. This slide deconstructs the system. We start with a crude reaction mixture in a tube or vial within an auto-sampling system. That reaction mixture is pumped through a large diameter purification column where the target analyte is separated from other compounds and impurities. After exiting the column, the separated components, including the purified target analyte, are detected. We collect individual peaks of interest in a fraction collector, and waste is discarded. But as we think about the practical purification operations, we need to keep in mind why we are doing the purification. We want to answer a specific set of questions to be successful in the next stage of the drug discovery workflow. In common purification laboratories, you're often asked to provide purified material for another laboratory to perform sensitive testing within the drug discovery workflow. For example, you may be asked to purify a library of compounds for a bioanalytical screen, or a series of singletons. In either case, there are questions that need answers prior to starting any purification experiment. The answers will ultimately define the purification method. How much compound is required for the next experiment? What is the mass required for the next experiment? This leads to questions like, what is the required purity of the compound for the next experiment? Or, what is the solubility of the purified material? Then, what amount or volume of starting material is required for me to begin the purification now that I know how much and at what purity is needed at the end of the purification? What is the solubility of my starting mixture? What is the complexity of my starting material? What are the chromatographic properties of the compound and other starting materials or impurities? And how quickly is the purified compound needed? That is, what are my speed, turnaround time, and workload requirements? Turnaround time means how quickly does the sample or compound need to be purified? Is it 1 hour, 2 days, 1 week? The time that the chemist has to do the separation can make a difference on whether he or she performs a quick or exhaustive review of each possible step. With the basic experimental questions defined, we can start to think about the correct experimental levers to pull to ensure we meet our experimental goals. From the previous slide, once the compound and mass quantity required are known, then we can determine the amount of total mass load required and select the column required. We want to load a sufficient amount of sample to concentrate the crude reaction mixture and enable sufficient quantity for the next experiment in the drug discovery workflow. Additionally, we want to keep the sample concentrated by using the smallest column possible. This will reduce the cost of the column and solvent and will reduce runtime. Using a smaller column also simplifies the recovery because the fraction volume is reduced, making dry down time that much faster. Also, smaller volumes reduces the number of collection tubes needed to hold the purified compound. There are two ways to do the purification efficiently. We can use the same method for every sample using a standard protocol, or for more difficult samples, we can develop the method by optimizing the separation conditions. In many operations, prep users may work with standard protocols, and only if necessary, they will need to optimize or adjust a method to achieve sufficient resolution. For standard protocols, sometimes referred to as open access, users will normally select a pilot column and conditions based on their compound, starting materials, and impurities. They'll perform a pilot run and evaluate whether they have achieved the resolution required for sufficient purity. If sufficient to achieve purity requirements, they will scale up the separation and perform the purification on a prep system with the same conditions and column chemistry. Where standard methods are not in place or insufficient to meet the resolution and purity requirements, users may start with a standard gradient pilot run at analytical scale, and from the results, make adjustments to achieve sufficient resolution to ensure sufficient purity for subsequent experiments. They will then scale up this optimized method on a prep system, perform their purification, collect their samples, and evaluate purity. It's important to note that instead of having this binary option in which we work with a standard protocol and optimize if we need higher resolution, we may move immediately to what we'll refer to as the ideal workflow. I will talk more about this when I speak about optimizing your purification for better resolution. This slide shows a generic standard protocol that can be used as a starting point. In this example, we have two mobile phases, aqueous mobile phase A and an organic mobile phase B. As a suggestion for a standard protocol, go quickly from a low percentage of B to a high percentage of B. We start at 95% A and 5% B, and within the first 4.5 minutes, or 9.1 column volumes, we step to 5% A and 95% B. This allows us to survey what the crude mixture looks like and whether or not we have to develop a method to isolate the compounds of interest. A 10% per column volume change in gradient slope is a good place to start for small molecules. When these conditions don't work, we can optimize the separation conditions at analytical scale and then transfer them to a prep column. Optimizing the separation conditions really means improving the resolution and increasing the mass capacity. I will focus the rest of my talk on these two topics, beginning with improving resolution. If we think about chromatographic resolution in the most basic sense, it is simply the width of two peaks relative to the distance between those peaks. If we can make those chromatographic bands narrower or further apart, we can improve resolution. Here's an example of improved resolution. Improving resolution means getting the product away from the other peaks that are co-eluting with the product or very close to the target compound. You can see in the top chromatogram that the peaks are poorly resolved and co-elute. The bottom chromatogram represents much improved resolution. For purification applications, moving the peaks further apart will allow us to load more material, ultimately decreasing the number of runs needed to get enough material for the next experiment, and at the same time increasing the yield and the purity. Resolution can be expressed mathematically in the form of the resolution equation. The resolution equation is comprised of physical and chemical parameters. These parameters are efficiency, selectivity, and retentivity. Selectivity and retentivity are chemical factors that have historically been the easier parameters to manipulate to improve resolution. These parameters can be affected by changes such as temperature, mobile phase modifier, composition, or column chemistry. Efficiency is a physical parameter that is more difficult to manipulate due to its square root dependence. For example, a 9x improvement in efficiency is only a 3x improvement in resolution. However, efficiency can have a significant impact on resolution if the particle size is very small. UPLC focuses on improving resolution through gains in efficiency by utilizing 1.7 micron particles. It's easier to understand how these parameters affect resolution if we think about how these three terms are represented chromatographically. Efficiency, or N, is a measure of band broadening in a separation. Increasing N makes the peaks narrower, increasing the resolution, as you can see by comparing the top chromatogram to the second chromatogram. Note that neither selectivity or retentivity changed between these two chromatograms. Increasing the retentivity, or K prime, increases the resolution, but makes the peaks broader, often at the expense of sensitivity, as you can see by comparing the initial conditions and the third chromatogram. If we increase our selectivity, or alpha, we increase the resolution. The peaks are taller and only slightly wider, as you can see by comparing the initial conditions and the last chromatogram on the screen. So let's start with efficiency. How do we increase efficiency in purification? One way to increase efficiency is to decrease the particle size. I spoke earlier about the fact that UPLC utilizes 1.7 micron particles to increase efficiency. But what about particle sizes relevant to purification applications? As you can see in the chromatograms represented here, by decreasing the particle size from 10 microns to 5 microns, we are able to better resolve the small peak indicated by the arrow from the main peak. This is because efficiency is proportional to 1 over the diameter of the particle, represented by the equation in the corner. Remember, using a smaller particle size makes the peaks narrower, the definition of increased efficiency, but not necessarily further apart. Also, remember that going to smaller particle size will lead to an increase in back pressure and an increase in the cost of the column. Another way to increase efficiency is to increase the column length. As you can see in the chromatograms in this slide, by increasing the length of the column from 50 millimeters to 100 millimeters while keeping the particle size and the internal diameter constant, we are able to better resolve the circled front peak from the main peak. But we have to be aware that increasing column length also increases the back pressure, runtime, solvent consumption, and the actual cost of the column. Next, how can we alter retentivity to improve resolution? Remember, retention is a measure of how tightly a compound is bound to the stationary phase. Changing retentivity can be achieved by altering the column chemistry, the mobile phase, or employing a gradient elution protocol. We are all very familiar with the fact that for hydrophobic compounds, a C18 column is more retentive than a C8 or a C4 column. For hydrophilic compounds, we would choose a column that gives us good polar retention, such as an Atlantis T3 or Hillic. We also know that mobile phase properties impact retention. High concentration of organic will reduce retention. Low concentration of organic will increase retention. It is also important to consider eluent strength. Acetonitrile is a stronger eluent than methanol, and isopropanol is a stronger eluent than acetonitrile. However, today I want to focus on modifications to gradient elution as a mechanism to change retentivity. That is, we can change the retention of a compound by modifying the way the compound elutes in a gradient. So let's take a moment to consider the different types of gradients for purification. As you recall from earlier, we said that the purification workflow could either rely on a standard protocol or an optimized protocol. The optimized protocol being employed when the standard protocol is insufficient. In the following slides, I will present a third option that obviates the need for the binary pathway, something we'll refer to as the ideal protocol. We are probably most familiar with the linear gradient, which has a constant rate of change throughout the run. In this example, we increase %B from 0 to 50% in 43 minutes, or increase by 2% per column volume. When we consider a segmented gradient, we preserve the beginning and end of the gradient, but slow down the middle segment of the gradient around where we know our target compound elutes. The slower rate of change of acetonitrile per column volume moves impurities away from the target compound. Increased resolution around the target compound means that we can achieve better purity in the separation. In this example, we increase percent acetonitrile by 2% per column volume for the first 20 minutes, then make the gradient more shallow in the middle of the run from 20 to 40 minutes around our target compound, at an increase of 0.5% in acetonitrile per column volume. At the end of the run, we return to our initial gradient conditions, 2% increase in percent acetonitrile per column volume. And finally, focus gradients very quickly ramp up to a percentage of B approximately 3 to 5% below the expected elution percentage of the target compound. At that point, the rate of change of B per column volume decreases to move the closely eluting contaminants away from the peak of interest. Once the target compound is eluted from the column, we can ramp the gradient to very high organic to wash the column and re-equilibrate the column for the next run. We can see the utility of using a focus gradient on this slide. In the first chromatogram, we increase the percent organic from 5 to 50% in 5 minutes. This is a rather steep gradient. In the second chromatogram, we start at 13.5% organic because we did an initial quick ramp as is typical of a focus gradient. Then we increase percent organic from 13.5% to 23.5% in the same 5 minutes that we ramped from 5 to 50% in the top chromatogram. That's a rather shallow or focused gradient. Here, we have moved the compound of interest further away from its closely eluting neighbor. We can obtain better purity without increasing the runtime. Here's an additional example of comparing a traditional linear gradient to the focus gradient in preparative HPLC. In this case, we achieved several benefits. First, we increased resolution between our target compound and some impurities, as you can see by comparing the tall main peak at 10.6 minutes in the top chromatogram and 4.9 minutes in the bottom chromatogram. This has been achieved because we have used a shallower gradient compared to the traditional gradient method. Second, you'll notice that we shortened the prep runtime and therefore increased throughput. And third, we have reduced amount of mobile phase, which leads to lower cost. As described earlier in the presentation, here is a high-level view of a traditional HPLC purification workflow. In our example, Sets of reaction mixtures would be screened to determine if acceptable purity and recovery can be achieved. If yes, the scientists would conduct a loading study and scale up the screening method for a purification run. This would represent the standard protocol mentioned earlier. If no, more optimizing is needed. This represents the optimized protocol we spoke of earlier. Then, as the target compound is collected, a confirmation analytical run is completed to verify purity. The problem is that all these steps take time and cost money. Laboratories are looking to further increase their throughput if possible. What if we can reduce the number of steps even further? What if we could jettison the typical binary option of standard versus optimized protocol? If we take another look at our workflow, starting with the reaction mixture, is there a way to speed up the screening step? There are three elements in improving throughput. First, many laboratories are moving to Acuity UPLC systems for faster screening and added resolution. Second, for the scale-up step, we want to move directly to a focus gradient prep run to create a fast and more efficient preparative separation. We will present a calculator tool that will assist in scaling from sub 2 micron columns to prep columns. And third, we can move quickly from our analytical screening step to prep by using exactly the same column chemistry in both analytical and prep column formats. This slide shows the various calculations needed for properly scaling up a pilot screening gradient to a focus gradient for a prep run. I'm not going to go through these equations in detail because lucky for us, Waters has developed a focus gradient calculator tool available online. It's important to note that calculating the focus gradient is not just a matter of visually determining from the chromatogram at what percent organic the target compound elutes in the screening gradient. The differences in system and column volumes must also be taken into account to properly calculate the actual elution percentage of the target compound in order to effectively transfer the separation to a focus gradient. From the previous slide, we can calculate the gradient slope of the pilot screening run, which is expressed as percent change in organic per column volume. We've seen the benefit of making a shallower prep gradient run for greater resolution and possibly greater mass loading. To achieve this, we use a slope that is 1/5 the pilot gradient slope. The focus gradient segment should start at an organic concentration that is 3 to 5% below the elution percentage of the target compound and end at an organic concentration that is 3 to 5% above the elution percentage of the target compound. As you can see, this is a lot of steps, so we developed a focus gradient prep calculator to simplify the entire series of calculations. This is a screenshot of the Online Waters Focus Gradient UPLC to Prep calculator, which is designed to help determine the focus gradient needed for the purification run from the screening method and target compound elution time. This calculator is available at waters.com/prep calculator. We will next review how to use this calculator. To use this calculator, all we need to know is the system dwell volume for our respective UPLC and preparator systems, the column dimensions and particle sizes for the UPLC screening column and the scaled up equivalent prep column, and our chosen focusing limit. Remember we said that our focusing limits should be between 3 and 5% of the percent organic needed to elute the target compound. Additionally, we will need to enter the flow rate for our UPLC run, and the calculator will automatically determine the appropriate flow rate for the prep run based on scaling to the prep column dimensions entered above. The only piece missing is the target peak retention time from the analytical run. Here's an example of a low pH screen using the Acuity UPLC CSH C18 column, where the analytical chromatogram of the pilot screening run provides the target peak retention time. You can see in this screening run that the retention time of the target peak is 1.32 minutes. We will enter the screening target peak retention time into the calculator. This completes the values needed for the calculator to provide a focus prep gradient table, which we can use to perform an optimized preparative separation. Here is the low pH example again, where the top chromatogram is the pilot screening run that we saw earlier. The second chromatogram is the focus gradient purification run, calculated from the focus gradient calculator. This run utilizes X-Select CSH-C18 with 0.1% formic acid, the same column chemistry and mobile phase as used during the analytical UPLC run. On the bottom is a confirming analytical run for purity. You can see that we properly scaled from an analytical UPLC screen to a preparative run using a focus gradient. So far, we've covered how to improve the efficiency and retentivity of a purification method. Next, we want to address selectivity. Selectivity reflects the interaction among the bonded phase, the mobile phase, and the solute. Changes in organic solvent, mobile phase modifier, mobile phase pH, temperature, and column changes all affect the selectivity. So let's focus on how changes in column and mobile phase can change selectivity. Changes in column selectivity impact the peak shape, retention, and elution order, as is evident when you see how peak number 7 changes when it's run on different columns. Here, you see that peak 7 moves further away from peak 6 when switching from XBridge C8 to XBridge Phenyl. When we change to XBridge Shield RP, we flip the elution order of peak 7 and 6. Switching to XBridge C18, we revert to the original elution order as with C8 and Phenyl, but you see a much greater separation between all peaks. In addition to changing the column chemistry, different organic solvents can also change the selectivity to improve resolution. See how peak 4 changes when the mobile phase is changed from acetonitrile to methanol, and how peak 7 changes when we change the mobile phase from a methanol back to acetonitrile. In acetonitrile, peak 4 elutes prior to peak 3. In methanol, peak 4 elutes after peak 3. In acetonitrile, peak 7 elutes between peaks 5 and 6. In methanol, peak 7 elutes between 6 and 8. Again, something that we all know but tend to forget when developing purification methods. Changing the mobile phase modifier changes selectivity as well. This acidic compound changes from eluting late in the gradient in TFA to early in the gradient when the modifier is changed to formic acid. Also notice the change in the elution order of an impurity peak highlighted with an asterisk. Over the last few minutes, we talked about the basics for improving resolution. We talked about increasing efficiency by decreasing particle size or increasing column length. We talked about altering retention, which can improve our ability to purify our compound of interest through column selection, mobile phase, and gradient slope. Most importantly, we discovered that we can use an ideal workflow based off the focus gradient protocol to improve retentivity and thus resolution. Not only is our resolution improved, but we can perform our preparative runs in shorter times with less solvent and thus at a lower cost. This ideal method also saves valuable method development time. Lastly, we saw that selectivity is a powerful tool for improving resolution. We saw how column choice, mobile phase choice, and mobile phase additives can improve resolution, which in turn will allow us to achieve higher purity of our target compound. These things also have an effect on mass capacity, which is the final section of this seminar. How much material we can load on a column is directly proportional to the volume of the column, which is determined by the column size and volume of the column packing material. That is, the column volume is a fundamental limit to the amount that can be loaded. Sample diluent injection volume also play a role in how much we can load on a column, but we won't address that today. We will also touch on operational considerations for achieving our desired mass capacity. These include the column chemistry, use of mobile phase additives, and the type of gradient. Today, we will talk exclusively about column chemistry and matching the appropriate mobile phase pH to that chemistry. The Waters mass loading table can be a very useful tool to determine where to begin in scaling up a preparative purification. For each column dimension, what is provided is a reasonable estimate of the total mass load per injection in milligrams. Equally important are both the reasonable flow rate and the reasonable injection volume for each column internal diameter. This chart establishes an excellent starting point. Please note that there are some additional considerations when put into practice. As stated on the PREP OBD wall chart, the final capacity may depend on the retention, sample mixture, how much resolution is needed, loading volume, diluent solvent strength, and the solubility of the compounds. We are all familiar with the PREP scaling equations, simple proportionalities that help us to determine how much we can load on a column and how to operate. To make it easier, we can use the Waters column back pressure and mass loads calculator to help us determine the right size column when scaling up from analytical scale. To use this calculator, use the LC column A section to enter your analytical column conditions, including the inner diameter and length of the column, the particle size, the solvent, and the flow rate. Next, enter the mass load and injection volume for your analytical run. For the LC column B section, you can enter different PREP column dimensions and particle sizes to see how the load and injection volume from analytical scale should scale to PREP. For both the analytical and PREP column, the calculator displays a calculated column-only back pressure. Lastly, you can see recommended minimum and maximum injection volumes and flow rates for each type of column based on the information you entered. We also have a calculator for tubing back pressure and splitters, analytical to PREP gradients, and as mentioned previously, the focus gradient calculator. Finally, let's investigate column chemistry and pH for increasing mass capacity. To do so, let's return to one of the goals of preparative chromatography. We want to know how much sample can be loaded onto the column without losing the required resolution and still be able to achieve the required purity when collecting the sample. Previously, we examined column size as a fundamental limit to mass load. But did you know that column chemistry and other chemical factors can greatly influence mass load? Let's now turn our attention to column chemistry and select a column that can offer high mass loading capacity for our analyte of interest. For example, not all C18 columns are the same when it comes to mass load capacity. We want to select a column that offers high mass loading for a wide range of compounds. Let's look at loading differences between acids and bases at different pH values via the classic retention map. Low pH is suitable for retention and loading of acids. High pH is suitable for retention and loading of bases. For purification applications, we want to increase our loading capacity while maintaining suitable resolution and thus purity. However, we usually separate bases at low pH, but the reason we do so is different than the reason for separating acids at low pH. Acidic compounds are separated at low pH to suppress their ionization. However, bases remain fully ionized at low pH. We run bases at low pH to suppress silanol activity on the silica packing material, thus eliminating peak tailing. We've always known that we would get very good separation of bases if we suppress their ionization by running at high pH. Historically, we could not run at high pH given the limitations of standard silica columns. At the higher pH values needed to transform bases into their non-ionized form and thus increase their retention on a reversed phase material, the silica would quickly dissolve. However, with the invention of BEH particles and their subsequent evolution over the last 20 years, we have a packing material capable of withstanding the high pH needed to run bases in their non-ionized form. As you can see from this retention map, the non-ionized basic compounds will have higher retention. Importantly, in many cases, the higher retention will allow the compounds to elute later in the separation at a higher percentage of organic solvent. More volatile organic solvent will speed up the dry down time, thus improving the overall speed of the purification workflow. Let's look at an example of scaling the separation of bases at low pH. At low pH, as we load more material from 1 to 10 to 20 milligrams per peak, resolution and peak shape suffers. The peaks tail very badly, running into one another. Expected loading capacity is only a few milligrams per peak. In contrast, when we load the same sample and use the same column chemistry at high pH, we have better resolution between the three compounds at all injection levels, even up to the point where we are injecting a milliliter. While we are getting 20 milligrams of each peak, we still have a flat, empty baseline between the separated molecules, far better resolution at a far higher mass capacity. Finally, the compounds elute at a higher concentration of acetonitrile. It is easier to recover the compounds since a smaller volume of more volatile solvent is being evaporated. In summary, use low pH for loading acids and high pH for loading bases to increase the mass capacity of the column. On the left, by lowering the pH from 10 to 7 to 2.3 for acidic compounds, we are able to increase the mass capacity by 3 times. On the right, by increasing the pH from 2.3 to 7 to 10 for bases, we are able to increase the loadability by 23 times. We can achieve loading at high pH with a high pH stable packing material like XBridge. Because we've increased retentivity, we can elute at higher organic concentration, thus reducing the dry down time and thus the turnaround time. During this presentation, we revisited the basic definitions of the purification process and purification experiments. We touched on basic experimental parameters and defined the typical binary protocol pathway, standard and optimized. We saw in cases of optimizing the protocol, what we really wanted to do is improve the resolution and increase the mass capacity. To improve resolution, we spoke about the effects of particle size and column length on efficiency, the effect of column chemistry, mobile phase, and gradients on retentivity, and the effect of column chemistry and mobile phase on selectivity. Importantly, we saw that we can jettison the typical pathway between standard and optimized protocols and instead start with an ideal protocol based on scaling up to a focus gradient. This results in significant method development time savings and material cost savings, all the while improving resolution, speed, and purity. Lastly, when speaking about mass capacity, we address the fundamental limits imposed by the physical characteristics of columns. We then address column chemistry considerations for improving mass capacity. At the end of the day, we hope that these fundamental principles help lead to better yield and higher purity in your day-to-day purifications. Thank you for listening.